Now we want to start solving problems using Gauss's law. So these are the problem-solving strategies for Gauss's law. And it's a three-step process. Do you have to follow exactly what I'm doing? Of course not, but you have to hit all of these points. So here we go. So the first step that you got to do is that you got to pick a good Gaussian. There's two conditions that have to be applied. One is that you have to have a symmetry condition, and another one is a dot product condition. And I'll go over these in a minute. And then in the next lecture, I want to go over step 2, which is to evaluate the enclosed charge dq, q enclosed. And then finally, we wrap it all up together and put step 1 and step 2 together to get the final electric field expression. Step 1, picking a good Gaussian. So what is a good Gaussian? A good Gaussian does one thing only. So it takes our flux, and then we perform the dot product. And as a consequence, we have a flux integral that now is equal to E cosine times dA. So a good Gaussian does what? It removes the electric field function and the cosine theta from the integral. So its whole goal here is to remove this from the integral. And when it does that, it does it the following way. So it removes the E field function because a good Gaussian is a constant E field surface. Using symmetry. That's why it can remove it from the integral. The other thing here is that now the value of the cosine function is due to the enclosed charge. And it's also a function that's generated by the dot product. But the value of the cosine function really tells us about whether we have positive flux or negative flux. So let's go through both of these situations. So the first thing I want to look at is I want to look at the symmetry condition. Because of the high degree of symmetry that's required, we can only look at three surfaces. And when we look at these three surfaces, we say that the key point is that the symmetry of the charge distribution is then equal to the symmetry of the Gaussian. So this turns out to be really crucial. And because this is crucial, that means that we can only do it to a few charge distributions. So there are only 3 possible charge distributions. Where one can remove the electric field function from the integral. And this is if you have that the charges are spherically, cylindrically, and planar symmetric charge distribution. If it's not one of these 3, then it's easier to use Coulomb's law. So this is a highly specialized tool. So now let's try to put stuff together here, and let's start off with a sphere. So let's imagine that we have a spherically symmetric charge distribution. So picture-wise, I imagine that I have a uniformly charged sphere. And so when I'm looking at this, I see a solid sphere, and in this case, it's going to have a uniform charge distribution that looks like this. So immediately I look at the charge distribution, and the charge distribution, the symmetry of the charge distribution has to be the symmetry of the Gaussian. So when I go to look at this thing, these guys have to go hand in hand. Once again, the symmetry of charge must be the same as Gaussian. So when I'm looking at this thing, now I could come in and look at my Gaussian. So then my Gaussian then encloses this sphere. And so this guy right here is this one here is a constant E field surface. And that is, of course, my Gaussian. It has to be the same shape as the charge distribution. So in other words, so when I look at my field poking out of the Gaussian, I'm seeing a uniform field at this point here. And then this guy here is a constant in magnitude everywhere. And so when I'm looking at this Gaussian here, we then say that this guy has some radius r. So the Gaussian has a radius r. Now, since this is a constant E field surface, we can remove it from the integral. So when I'm looking at this, I'm looking at my flux. So then my flux is E dot dA, but now I'm integrating over a spherical shell. It's not a solid sphere, it's a spherical shell. And we see here, as I continue to do this, this is going to be E cosine of theta dA. So now it's a constant. So then I'm writing this guy out. And so then I'm left with the area of this spherical shell here, dA, which I can then simplify the calculation and then just say that what I really mean by this is that I have this is what Gauss's law tells me here, is that if I look at the flux of a spherical shell, that shell is E of R cosine of theta, and then that's the area of this spherical shell. That is a really, really powerful statement. And the reason why this is a powerful statement here is that look what the flux depends on. As a consequence, what does the electric field depend on? You're seeing here is that the electric field depends on the shape of the Gaussian, right? So what's important about this relationship is that the electric field is proportional to 1 over the area of the Gaussian. That's what determines the electric field. By the way, I should have said where A of a spherical shell is then 4 pi r squared. Now let's go to cylindrically symmetric charge. This one is a tad trickier. And so what happens here is that if I have a cylinder, we have to worry about the endpoints of the cylinder. So if we're talking about a spherically symmetric charge distributions, we can't talk about the endpoints of the cylinder. So symmetry can only occur if we cannot see the endpoints and field fringing, right? We cannot see the endpoints and field fringing. So in essence, therefore, only infinite cylinders make sense since we can't do that, since we can't look at the ends. But you're going to see that the Gaussian is going to have to look at the endpoints. So now let's look at a cylinder. So you can imagine that I have a cylinder. And again, the symmetry of the charge distribution must also be the symmetry of the Gaussian. So now when I'm looking at this thing continues to go forever. And so, but we have a uniform distribution. So once again, we can't see the endpoints. So then, according to what we've been saying here, the symmetry of the charge distribution must be the symmetry of the Gaussian surface. So now we then enclose this cylinder. And of course, this cylinder just keeps going on, this Gaussian. So then I have this enclosure here. And inside, we're going to look at this thing, but we have to agree that the only way we're going to get an electric field that's constant if we look at the sidewalls. The sidewalls will then can have an E field surface that's a constant. But unfortunately, it's not going to be that simple. We have to, for the Gaussian, we have to look at the sidewalls. So here, I would say that this is the end cap. And then right here, this is the sidewall. Not the sidewalls. Let's not do that. Let's call it curved walls. So we'll have to consider both of these when we look at that. But the hint is that that electric field better be zero at the end caps. Right? They better be zero. Otherwise, we see the fringing. Okay, so the cylindrical surface, maybe, let me be careful here. The cylindrical shell only looks at the flux through the curved walls of the cylinder. So the flux integral reads like this. So I have a flux. And if I look at that, I'm integrating over a cylindrical shell. So when I look at the shell of this E dot dA, what I'll show here is that this is going to be an integral of the end caps of E dot dA, plus this is going to be the integral over the curved walls of E dot dA. And what we will show here is that this term will go to zero. And so the only thing we care about when we apply Gauss's law is that because it's a Gaussian surface, I will be able to remove it. So this reads, so if I put this all together, then I'm going to say here is that the flux of a cylindrical shell is then going to be E of r cosine of theta, and this will be the area of the curved walls. Again, look at the electric field. The electric field is inversely proportional to the area of the Gaussian. It's about the space. Where if I'm looking at the side walls or the curved walls, you could imagine that I have this. So the length here has to be the circumference. And then this guy is going to be the length of this guy here. So when I'm looking at this, I'm talking about this guy right here. And you're going to see that this area, the area of the curved walls, is then going to be 2 pi RL. Now, the last one that we want to look at is we want to look at planar symmetric charge distributions. So now we have planar symmetric charge distributions. Once again, this is very, very similar to what we said in the previous example here with the cylinder. Symmetry only makes sense if we can't see the endpoints. So if I come back up here, I'm going to look at that. Symmetry only makes sense if I can't look at the endpoints. So it's the exact same statement. If I get close to the edges, then it's going to be a problem. So let me copy this. Let's see if it copies right this time. And it does. And here we go. Symmetry can only occur if there's no fringing. So in this situation, we then say similar to the cylinder only infinite thick planes can do this, right? They're the only ones that fit the bill. So now I imagine that I have something like this. So I have a shell, not a shell, but a charge distribution. And I'm looking at something like this. So if I'm looking at this, remember, I cannot be close to the endpoint. So it just keeps going on. So if I look at the charge distribution here, then I'm going to see that I'm going to get a uniform charge distribution that looks something like this. And what we're saying here is that we can't see the edges. So then, as we said before, the symmetry of the charge distribution must be the same as the symmetry of the Gaussian. So if I'm looking at this, what I'm going to do is that I'm going to do sort of like a side view. So if I'm looking at this here, I have this thick plane. And what I know about this plane here is it has this charge that we're looking at right there that's uniformly distributed. Now remember, if I'm have symmetry in the plane, and if I stand right here, then no matter where I go, that's a constant field. So when I look at my Gaussian, what I'm really doing is that I'm doing this. I'm forming this guy right here. And you could see that I'm just trying to set this up exactly the same way. So then you could imagine that this guy is coming all the way through. And here's my Gaussian shell here. So if that's plane, the only way I can have planes here is on the top and bottom faces. So in other words, what this is telling me here is that we have symmetry. So then only the top and bottom faces have planar symmetry. Not the sidewalls. So then my Gaussian then says that everywhere I see this, I can have the same, I can have a constant electric field on these planes, where this is E is equal to a constant. So for Gauss's law, just moving along quickly here, we could then say that the flux of a cubic shell is then this guy, which will then be E cosine of theta dA, which then tells us that I could now write the flux of this guy as E sub r cosine of theta, the area of this cubic planes. And this is just the area of the plane here. So now the last thing that we got to deal with is the cosine term. So let's go do that. So now we're going to talk about the dot product condition. The origin of the cosine term is due to the dot product. As we already said here, we can write the flux in terms of cosine of theta, E of r, times the area of the Gaussian. So in this case, we could see here is that this is the term that we got to focus on. So the cosine term, as I already stated here, the cosine term tells us about the sign of the enclosed charge. Of course, inside the Gaussian, it turns out that there are three possibilities. And here they are. One, if they're parallel. If they're parallel, then that means that, so we have parallel E and dA. That implies that theta is equal to 0 degrees. If they're anti-parallel, then that implies here is that theta is 180 degrees. So those two vectors are in opposite direction. So in other words, I'm saying that if this is my direction of dA, then the electric field is going to be pointing in the same direction. Here, we're saying that the E field is in the opposite direction of the area vector. And then finally, we get perpendicular. And perpendicular implies that theta is equal to 90 degrees. So picture-wise, we then see, of course, that the area vector is going in that direction while the electric field is coming like this. In other words, we have a right triangle between them. So let's look at each of these cases here. So the first one that we're going to look at parallel E and dA imply outward flux. And that's theta equal to 0 degrees. So if that's the case here, so if E and dA are parallel, then we could say here is that the flux pokes outwards of the Gaussian. But we've already defined that outwards here is that this is only true for a positive enclosed charge. So if I have three surfaces, it's going to look something like this here. So if I have a spherical Gaussian, then that means here is that the electric field is pointing this way, and dA must also point in the same direction. If I have a cylinder, and remember, we only care about the curved walls. We don't care about the endpoints right now. And again, we have to worry about the edges. So we're not paying attention to the edges. So if I look at the curved walls, then I have an electric field that does this. And then finally, if I have a cube, then I'm looking at a cube that looks like this. The only thing we care about is these two planes right here. And so when I'm looking at these two planes, I can have an electric field that goes in this direction or in that direction, where my dA vector also points in the same direction like that. So now that I have that, I could then come in and just say, what is the flux read? So then, the flux reading is this. We have our flux. We then have our cosine of theta, but in this case, it's 0 of E of R times A of the Gaussian. And as a consequence, I get a plus sign. So let's do this right here. So that cosine gives me that plus sign. That's what the dot product condition gives me right there. So that's what we know. So when I look at this flux here, this is going to be the flux at theta equal to 0 degrees. Now I'm going to repeat the same process for 180 degrees. So I'll be a little bit faster here. So here, we're picking, in this situation, we had what? We had parallel, now we have anti-parallel. E and dA, and that really tells us that theta here is 180 degrees. So in this situation, what do we have? We have something different now. So if E and dA are anti-parallel, then that tells me here is the flux through the Gaussian is inwards. And because it's inwards, that tells us here that this can only be true for a negative enclosed charge. So if I come over here, let's see if I have that picture still. Nope. I'm going to come over here and take this, and I'm just going to modify this. Actually, I'm going to take all of this and just modify it lightly because it's the same thing effectively. So then I'm going to come over here and I'm going to do this. So the only thing that's different now is the direction of the electric field. What's happening to the electric field? The electric field now is pointing into the surface. And now we have a cosine of 180 degrees, but that's not going to give us a plus sign. It's going to give us a minus sign. So then this flux right here is for 180 degrees. So now the last one that we want to pay attention to is the perpendicular. So when I'm thinking about the perpendicular, what I'm really looking at here is that I'm saying here is that we have perpendicular E and dA. So now we're looking at angles of 90 degrees. So when I'm looking at this thing, it turns out that this is a bit trickier here. This situation can only occur to distributions with sidewalls. Spheres don't have sidewalls. So that means here with sidewalls, which implies only cylinders and planes or and cubes. So now here's what we're looking at. So let's look at a cylinder. So if I look at a cylinder, what am I seeing here? Well, I have a cylinder that's looking like this. So if I'm enclosing this charge here, I'm really now only looking at the end caps. Okay, so what you're seeing here is that right here and right here, these are the end caps of the cylinder. So when I look at the area implies that it's poking out in this direction, and this guy's going in that direction. But if I'm enclosing a positive charge, let's say, then the electric field is actually coming perpendicular to this. In other words, this is a right angle right there. And if I do a side view, it will be easier. So now what I'm looking at is that I'm looking only at the side of the Gaussian. Okay, so this right here is the end cap. So when I'm looking at the end cap, you can see here is that A is perpendicular and pointing out. And now the electric field is actually never going through it. As a consequence, that's 90 degrees. So that tells me right away that I'm going to have a cosine of 90, which is 0, which tells me 0 flux. The same thing happens with the cube. So if I look at the cube, here's what I'm seeing at. We only care about the sidewalls. So if I look at the cube, I'm looking at something like this. I only care about the sidewalls. So when I'm looking at the sidewalls, what am I seeing? I'm seeing the same type of thing. I have an area here, and I have an area vector pointing out here. So when I look at the electric field is actually perpendicular to this field right here. So if I'm looking at this, note that there are 4 sides. So if I now look at a top view of this, to try to make it more clear, here's what I'm seeing. So my top view looks like this. And so I'm seeing the electric field coming up. So if I'm seeing the electric field coming up, you could see here that I have 4 areas of each of the sidewalls. And they're all going to be perpendicular. So the flux reading is that I now have a flux, which is E dot dA, which is now cosine of 90 degrees of E of R times the area of the Gaussian. And in this case, that has to be equal to 0 for the flux at theta equal to 90 degrees. So when I'm looking at this 90 degrees is associated with this 0 right here. And so I know what the flux is. It's this guy right here.